Yeah, hello everyone. Today I will present our recent works on interpretable identification of undesignable RNA secondary structures. I'm Tianshuo Zhou, currently third-year PhD at Oregon State University. My advisor is Professor Liang Huang, who also gave another presentation yesterday on RNA design. So RNA design is the inverse problem RNA folding. We have talked about this in other presentations. So RNA folding is to predict the secondary structure from a given sequence, and the RNA design aims to find a sequence that can fold into the target structure Y. Because of the exponentially large search space, the RNA design problem is very hard, and a lot of methods have been proposed to generate a sequence from an input Y, but really little attention has been paid to the undesignability, so whether a target structure is really designable. So how we started this topic, it goes back to like one year and a half ago, when we were doing RNA design project to solve this benchmark Eterna 100 puzzle, and we came across this Eterna puzzle number 67, and we found that no matter what kind of algorithm we use, and no matter how many times we try, the design sequence would always fold into this Y prime instead of this target structure Y star. So at that moment, we just speculate maybe this Y star is undesignable, which means you can never find a sequence X that can fold into this Y star. So since then, we have developed a progressive series of algorithms and theorems to prove that some Eterna 100 puzzles are indeed undesignable, including this one. So we have two papers so far. One is published in Recom 2024, and another is available on arXiv. So today's talk will be split into part 1 and part 2 correspondingly. So in the part 1, we focus on the structure level undesignability, and in part 2, we further identify more local regions that account for undesignability. So this is overview of the part 1, our published paper. We propose the 3 algorithms, and here are some examples. So in the first example, we prove this target structure Y star right here is undesignable because there is another so-called rival structure Y prime that always has a lower free energy than the target structure Y for any possible sequence. And in the second example, this Y star is also undesignable because we can identify a small set of rival structures such that for any RNA sequence, at least one of the rival structures is more stable than the target structure Y. And finally, we have this algorithm 3, which proves the global undesignability by identifying undesignable substructures. And all the 3 examples come from the Eterna 100 benchmark. So now let's delve into the details. The first is the definition of undesignability. Target structure Y is designable under this unique MAV criteria if and only if we can find at least one sequence X such that the target structure Y star has the lowest free energy among all the structures in the ensemble or in the conformation space. Correspondingly, target structure Y star is undesignable under unique MFE criteria, means that this MFE criteria can never be satisfied. So for any possible sequence X, there would exist at least one competing structure Y prime that has a lower or equal free energy than the target structure Y star. So in other words, for sequence X1, there would be a Y prime 1 that's more stable than the target structure Y. For sequence X2, there would be a better Y prime 2. Sequence X3, there would be a better Y prime 3, so on and so forth. However, algorithmically speaking, we cannot enumerate all the possible sequences in the design space and find and to check whether there is such rival structure for each of them. Yeah, because of the huge search space. So to begin with, we consider a very special case, which is if we have this single rival structure Y prime, such that for every possible sequence X, this single Y prime always is always better than the target structure Y in the ensemble. So that's exactly our theorem 1. So if we can find such a single Y prime that's always better than the target structure Y for any sequence X, and then we assure the Y star is undesignable. So the point is to show the superiority of Y prime for any possible sequences in the design space. Circle back to our motivation example. How do we show that this Y prime is always better than the Y star? Again, we cannot enumerate all the sequences of such a length, but we observe that the Y prime and Y star, their structure is very similar. So the majority of their loops are overlapped because the free energy of a structure is the sum of the free energy of their loops. So when we take their energy difference, their overlapped terms would just cancel out. So at the end of the day, their free energy difference is only dependent on the non-overlapped loops or those very sparse critical positions. As a result, instead of enumerate all the possibilities in the whole sequences, we can just do it equivalently by enumerating those the nucleotide compositions in those very few critical positions. And it is definitely doable and extremely fast. So in our implementation, it only took like a few seconds, maybe 2 seconds to prove this, to prove like this Y prime is always more stable than Y star. So this Y star is undesignable. And here is a detailed description of our algorithm 1. So given a target structure Y, we first try to design it by using some existing RNA design methods. And if this sequence can fold into Y star, then it is designable. And otherwise, we use the MFE structure of this sequence and the candidate of the rival structure, and we compute the critical positions, and we enumerate the nucleotides on those critical positions, and we check whether this inequality from theorem 1 always holds. If it always holds, then the Y star is undesignable. And again, for this case, we just enumerate those positions. Other positions really doesn't matter for their energy difference. And here are some more undesignable cases identified by algorithm 1. So, all this four structure come from Eterna 100 datasets, and for each of the case we have a single Ryo structure which can be obtained by removing the colored pair. And even though algorithm 1 has very strong interpretability, but it assumes very ideal case, very special case, which is that the Y prime, the single Y prime is always better for all sequences. However, that's not always the case. More generally, usually when we try to get a Y prime, it more often is only better for it's better than the target structure Y star or more stable than target structure Y star for some of the sequences in the whole design space. And for the remaining design space, still this Y star has a lower free energy. So our second idea is to generalize to multiple Ryo structures. So the theorem 2 say that if we can identify a smaller set of Ryo structures such that for any possible sequence X, at least one Ryo structure from this smaller set is better than target structure Y star, and then this Y star is undesignable. So which means if the first Ryo structure is not enough to cover the whole space, we can find the second. And if two structures is still not enough, we can find the third, so on and so forth. So in our algorithm 2, we starting with an empty Ryo structure set and repeatedly sample sequence X from the remaining design space and fold X into a Ryo structure and adding the Ryo structure to the Ryo sets until the remaining design space become empty or the whole design space is covered by the current set of Ryo structures. And there is a Eterna puzzle, Eterna 100 puzzle, which proved undesignable by algorithm 2. So the left-hand side is the target structure, and the right-hand side there are 1, 2, 3, 4. There are like 8 Ryo structures. So for any possible sequences, at least one from the 8 Ryo structures has a lower free energy than the target structure. And there is another example, Eterna 100, the puzzle number 88. So the top left is the target structure, and the right side there are 9 Ryo structures. So for any time, at least one from the 9 Ryo structures is more stable, is preferred than the target structure. Yeah, even combined with algorithm 2, there are still some limitations. So first of all, they both assume the Ryo structure Y prime is kind of close to Y star in terms of the loops. Otherwise, if they don't share a lot of overlap loops, their critical positions would become many, become not enumerable within a limited time. And secondly is about the concept. So they only provide a global undesignability interpretation. So there is global Ryo structures. So our third idea is try to prove the global undesignability by identifying local undesignability. So there is another case, Eterna 57, which cannot be proved undesignable by algorithm 1 and 2. So for this puzzle, when we try to design it, we find the sequence, the final design sequence tended to fold into this Y prime. And because this Y prime is so distant from this target structure, so we cannot apply. We can apply to algorithm 1, 2, but it runs forever. So we have to come up with something new. So instead, we focus on this highlighted span, or we call it a substructure, and we fold the corresponding span in the sequence, the subsequence, with the constraint that the left-hand side and the right-hand side must be paired. The result is that the subsequence would be constrained fold into this rival substructure, and this rival substructure is similar to this target substructure, only there are two less hairpins. So we can apply algorithm 1 and 2 to this substructure and subsequence to show that this rival substructure is always preferred than the target substructure. And as a result, if we substitute this target substructure with the found rival substructure, and we can obtain a global rival structure that always has a lower free energy than the target global structure. So in our theorem 3, we say structure Y star can be proved undesignable if we can find a span, or find a pair bounded span that is context constrained undesignable. So this context constrained just means that the left-hand side and the right-hand side, they are paired. And the context constrained undesignable just means the rival substructure also needed to be pair bounded and always better than the target rival structure. And for our algorithm corresponding algorithm 3, we just enumerate all the base pairs in the target structure, and then we apply the algorithm 1 and 2 to the target substructure from I to J. But here we use the constraint folding for dealing with the substructure. And there are some examples, some undesignable Eterna puzzles identified by our algorithm 3, and the corresponding undesignable substructure is highlighted in green. And for each of this undesignable substructure, it has a single rival substructure. Again, this single rival substructure can be obtained by removing the colored pair. And there is a more complicated case. So this Eterna puzzle 81 is called a campfire. So this for this large puzzle, we show it's undesignable by identifying such a small substructure undesignable, and it has let me see, it has non-rival substructures. So for any nucleotides arranged upon this span, so at least one of the rival substructures is better than the target substructure. And we then applied our three algorithms to the Eterna 100, and using all kinds of RNA methods. So there are like 78 turns out to be designable using the ViennaRNA 2 folding model. And for the remaining, we can efficiently prove that 15 out of the 20 left are undesignable. And again, there is one more structure undesignable if we ignore some special hairpin parameters. So those parameters, they did not come from the experiment. They just come from some heuristic rules from human expert. And more interestingly, there is one more structure that's successfully designed while we are searching the rival structures. And we can see the algorithm is really fast. So usually they take like several seconds or minutes. And so after this work, there are remaining 5 structures in Eterna 100 datasets whose designability is unknown. But in the part 2 talk, in the part 2 later, I will our new methods, which is stronger, and we can further prove that 2 out of the 5 are also undesignable. So in total, there are 3 puzzles left whose designability is unknown. So brief summary of the part 1 talk. So we proposed 3 algorithms as well as 3 theorems. So basically, the essence is single Roy structure, multiple Roy structures, and undesignable substructures. And we applied to the Eterna 100 puzzles. And for the first time, we were able to show that 13 of the unsolved puzzles are actually like no hope, you cannot solve it using the ViennaRNA two-folding model. And so now I will proceed to the part 2 talk. So in the part 2, we take one step further to identify the smallest or minimal region within a structure that's causing the undesignability. So here are 2 examples from Eterna 100 puzzles. So there turns out their undesignability can really be constrained to those small regions. But if you further try to make the region smaller, and then it would be the smaller region would be designable. Again, here are brief motivation of the follow-up work. So for the previous 3 algorithms, they're already very strong, but still they are not perfect. So first, their interpretability only focus on the structure level or substructure level, and secondly, they cannot handle some very long, intricate structures, as I have shown. So the basic idea of this follow-up work is that we wanted to identify the minimal regions that really accounting for the undesignability. So this example we have seen it. So for this Eterna 52, its undesignability can come from these 3 loops. So it contains this multiple loop, this stacking loop or internal loop, and this external loop. And for this Eterna 96, its designability can come from any one of the 4 motifs. And each of the motif, it only have 2 loops. So a multi-loop and a hairpin loop. And more interestingly, those 4 motifs, they are actually equivalent. So later in the slides, I will show how we develop an algorithm to detect such equivalence or such isomorphism. So first is a definition of motif in our work. So it is very simple. It's just we define a motif M as a contiguous set of loops in a RNA secondary structures. So there are 3 examples. So the motif M1, it only contains 1 loop. The motif M2, it contains 2 loops, and the larger M3, it has 3 loops. So 1 multi-loop, 1 stacking loop, and another multi-loop. And we also generalize the undesignability definition. So a motif M star is undesignable if and only if for any nucleotide composition there is another competing or rival motif M prime that's has a lower free energy than the target structure M star. And how we validate a motif is undesignable. Again, we use this so-called rival motif method. So for this motif from the Eterna puzzle number 52, we take it out and running our algorithm, we can identify this single royal motif. So which means that no matter how you design it, for this part, we can find an alternative that is always more stable. And also when one royal motif is not enough, we can also find multiple royal motifs. So we take out this motif from the Eterna puzzle 81 is here left-hand side, and we identified 5 royal motifs. So for any design, at least one of the 5 motifs is preferred than the target motif. And the conception we proposed is called a minimal undesignable motif because we require it has 2 conditions. So first, the motif is undesignable, and second, it can't contain any other undesignable motif. It has to be, it has to be minimized, and you cannot shrink it more. So for the 2 examples we have seen, both of them are minimal undesignable motif. So they both have 3 loops. So if you remove any loop from, if you remove a loop from the 3 loops, the remaining would become designable. And there is a counterexample, which is a case from the previous algorithm too. So this undesignable substructure span, it is undesignable, but it is not minimal because we can find a smaller region within the span, a smaller motif that is undesignable. So one crucial property of such undesignable motif is that once we found it, we can use it to detect, to decide whether a larger motif or larger structure is undesignable. So if this undesignable motif star appears in another motif, a larger motif, and then this larger motif, of course, is also designable. So we have to come up with an algorithm or graph representation to be able to detect the existence of a motif within a structure. So in the beginning, we try to use this loop graph where each node represents a loop in the RNA structure, and each edge represents a base pair in the RNA structure. However, during this transformation process, some information are lost. So you can go from RNA structure to loop graph, but you cannot go from loop graph to RNA structure because the number of unpaired bases are lost in the loop graph. So we propose a new representation. We call it loop pair graph, where there are 2 kinds of nodes. So one kind of nodes still represent the loop, but another kind of nodes, they represent edge. So in this way, both loops and edge in the RNA structures are nodes in the graph, and the nodes are connected by edges according their adjacency in the according the adjacency of loops and edges, the loops and the base pairs in the RNA structure, and the number of unpaired bases are represented as the edge widths in the loop pair graph. So in this way, we can go from RNA structure to the loop pair graph, and then we can go back from the loop pair graph to RNA structure. So it is a bijection. So mathematically beautiful. So one interesting property of the ViennaRNA model or the nearest neighborhood NN model is that they have such property called rotational invariance, which means, so if we rotate a motif, by like 60 degree, 90 degree, the energy doesn't change at all. So here are examples to show the rotational invariance. So these two motifs, they come from the two Eterna puzzles respectively, and they're very similar. So this MA and MB, they both contain 3 consecutive boundary loops, and if you check their number of unpaired bases, the orientation is like 1, 0, 1, and the orientation of MB is 0, 1, 0. So at the first glance, so they're not equivalent, but actually you can rotate one of them by 180 degree, and then it becomes totally aligned with another. And so here are the diagram of their motif and the corresponding loop pair graph representation. And a counterexample is this motif MC from Eterna puzzle 88. So this MC, it also has 3 consecutive Bauch loops. But if you observe, if you count the unpaired basis is 0, 0, 1. So therefore, no matter how you rotate it, it can never be aligned with this motif. So using this loop graph representation, and it's very easy to check the identity by rotating the loop pair graph. And another example from this Eterna 86, so it has we found 3 undesignable motifs within this large puzzle. So turns out 2 of them are equivalent. They both contain 2 loops, 1 multi-loop and 1 hairpin. And again, at first glance, they have different orientation, but you can rotate one. You can rotate one graph by 120 degree, and then it becomes the same as the other. And finally, we have this bottom-up search algorithm to find to check the undesignability of all the motifs within a structure by the order of their cardinality of the loops. So the smaller motifs will be checked first, and the larger motif will be checked later. So once it's identified undesignable, and then we know that all the smaller one within it is already checked, so it would be minimal undesignable. And then we applied those motif identification algorithm and the loop pair graph, the isomorphism detection algorithm to the Eterna 100 datasets. So again, there are like 21 puzzles that's unsolved yet using the unique MAV criteria, using the ViennaRNA 240 model. And so in total, we found 37 minimal undesignable motifs, and 26 of them are unique. So, and in total, there are 18 structures from the 21 left are undesignable. And here are the visualization of the motifs. So we can see there are all kinds of visually appealing structures. And it's very interesting because some of them are very large, but their undesignability can be accounted by only very, very small region. For example, this gladius, and also for this interesting mutated chicken feet, it has three feet in 3 chicken feet, and each of the feet is undesignable. And yeah, there are another chicken feet. It has 2 chicken feet, so each feet is undesignable. And for this shooting star is also very smaller undesignable region. And some of the puzzles, it contain multiple undesignable motif. So this structure, it has 3 three undesignable motifs. And for this set pool, it has 8 undesignable motifs, but turns out it can be grouped into 2. So the four of this they are equivalent, and 4 of this they are equivalent. And again, the algorithm is very fast, so it's only around a few seconds, few minutes at most. And we further apply, yeah, because the Eterna 100 dataset, it is human design, it is artificial, so not from the native, not from nature. So we further applied our algorithm to the to the native structures from nature. So this dataset is called archive2 9-family dataset. So it basically contains 9 family of RNA from nature, and compared to Eterna, there are more puzzles. Is total like near 3,000 puzzles, and each family it has different lengths. Some of them are really long. For example, the 16S and 23S, they're like 1,000, 2,000, 3,000 nucleotides. And to our surprise, out of the 3,000 sequences, more than half of the native structures turns out to be undesignable under the ViennaRNA2 model, and the minimal undesignable motif, like thousands of them we found, and a lot of them are just repeated. So within each family, there are a lot of repeated undesignable motif. So in total, there are more than 400 minimal undesignable motifs we found, and we tried to construct it as a library. And there is a visualization of the minimal undesignable motifs in the 16S RNA family, and we can see not only the structures are kind of conserved across those homologous sequences, but also some of the undesignable motifs are also conserved, which is also very interesting. And yeah, here are just some more visualization of those motifs. So each motif they have boundary pair and internal pair, and usually those motifs those undesigned motifs they are small. And for this family, it has for this SRP family, it's a very large loops. Even some of the eternal loop can be large. But this is a longer family, and TMRA, GRP1, and some undesignable motifs with more than 3 open pairs. So to summarize, our follow-up work focuses on identifying the minimal regions accounting for undesignability. So it has stronger results, stronger interpretability, and a better visualization effect. And we propose the loop pair graph for representation and for isomorphism identification. And we have this bottom search order to check the motif one by one, and we apply the algorithm to both artificial Eterna 100 datasets as well as this natural archive2 datasets, and some of the results are really surprising. So especially for the archive2 dataset, so it really reveals the current Vienna2 model is not perfect because it cannot even design the natural sequences, the natural structures. And we believe our work provide a new perspective for inspecting the folding model, specifically the thermodynamic folding model, and there can be different directions from here. So we can apply the current algorithm to different to more folding model, like the Eterna fold, control fold, the new pack folding, and we can then try to enhance the folding model if we really want to avoid such undesignability results. And another thing that's because the Eterna benchmark is used to encourage RNA design method. So probably maybe we can use the undesignability results to to modify the current data sets and yeah, contribute to the community. So here are our two papers available online. So I think that's all my presentation, and now I can take questions.